So here we're going to take a look at a concept called the unit cell. The unit cell is the smallest little bit of stuff that we need to repeat to make a crystal and preserve all of its symmetry as well as its chemistry. So I'm just going to draw a little cube here. And actually not just for the sake of illustration, but because we're going to look at something called polonium. And we're going to look at this metal polonium because it is the only thing that I could find that is a metal that has the simple cubic packing. So you might remember from another video, the simple cubic packing would be the case where these atoms line up with one another. With other forms of packing, if we line up the atoms like so, we can get a slightly tighter packing by allowing the next layer of atoms to line up into these divots over here. But in sort of a simple cubic packing, it's not a closest packing. It's this kind of simple case where we add atoms directly on top and to the side of one another instead of taking care of those divots. And so it's not quite as efficient, but it works for polonium. Apparently it's a rather rare situation because most metals will take advantage of those divots and form in something like HCP or CCP, which we discuss in another lecture. Anyway, let's take a look at polonium. For polonium, we're going to use a formula where the total number of formula units Z is going to be equal to the density times the volume times Avogadro's number divided by molar mass. So let's talk about what this fellow Z means. This Z is the number of, well, in this case, atoms. We just have polonium and nothing else. It would be the number of formula units in the unit cell. And so we're going to take polonium as an example. In this case, because we only deal with polonium atoms, this will literally be the number of polonium atoms in the unit cell. So how many atoms of polonium do we need to create this kind of simple cubic pattern? Well, we need to know the density, the volume, the value for Avogadro's number and its molar mass. We'll erase the chalkboard and take a look at this calculation. So we'll just repeat the equation here. This is rho times V times N divided by M. So let's take a look at all these. Let's take a look at density first. So density, we can look it up for polonium. It is 9.1 grams per cubic centimeter. Let's tack volume now. So for volume, if we have a simple cube like this, then we need to know the length of some edge. Let's just call it A. That's the way it would usually be given. If we have something that's a simple cube, we would have axes of A1, A2, A3. We don't have to worry about them. They're all the same. So we just have a simple cube length A, and this is A, and that's A, and then if we want the volume, then the volume would be simply A cubed. So the value for A is about 3.336 nanometers. But notice that we have this in centimeters, so we're going to convert A to centimeters, and it'll be 3.36 times 10 to the minus 8 centimeters. That's just a little bit easier because this is in centimeters, and so we need those units to cancel. Not just easier, but necessary. So that is A. So A cubed is volume, and so A cubed is equal to this whole thing taken to the third power, and that'll give us 3.793 times 10 to the 23, and that would be in cubic centimeters since we're cubing that unit there, centimeters instead of nanometers. And then N, it has its usual value, 6.022 times 10 to the 23. I usually describe this as being unitless, but it really you can't think of it as being the number per mole, and we're going to need that to see everything cancel out. So, one last value we need is the denominator here, m in the molar mass, essentially the atomic weight, because we only have one atom, is 209 grams per mole. So let's plug that into the equation. So we're going to erase the chalkboard. What is Z? Z is equal to 9.16 grams per cubic centimeters, and then that will be multiplied by 3.36 times 10 to the minus 8 Oh, that's not what we want. Not 3.36. We want the volume. 3.793 times 10 to the 23. And then that is in units of cubic centimeters. And then that'll be multiplied by n, 6.02 times 10 to the 23. And that'll be divided by molar mass, which is 209 grams per mole. Let's take a look at the way the units cancel out. We've got grams up here, it'll cancel with grams. And we usually don't write units with it, but if we write it as 1 over mole, we've got a 1 over mole left over here, 1 over mole, 1 over mole. Those cancel each other. Cubic centimeters cancels with cubic centimeters. And yes, we've got the right value for volume there. Don't put the linear value for edge length. We want the volume. And when we do that calculation, we get the number 1. So it means that for polonium in its simple cubic configuration, we only need 1 atom of polonium in our unit cell. So 1 atom of polonium in the unit cell. How could that be? Couldn't we take 1 atom and distribute it in any number of ways and make any kind of pattern, right? Couldn't we take 1 atom of polonium and make this kind of pattern and then this kind of pattern? Or could we take 1 atom and make this kind of pattern, right? Or couldn't we take 1 atom? Well, the answer is no. When we take a look at the unit cell, what we mean is something like this. And we'll show you how that answer of 1 atom works out. Now you might look at this. This is sort of an expanded view of a so-called simple cubic structure where the atoms are sitting on top of one another, and we're just going to shrink down the atoms so we can look at the geometry of how they're arranged. So when you take a look at this kind of fellow here, keep in mind that those atoms are being shared. So let's take a look at this guy over here. There is going to be another cube that is stretching out over here. We'll draw it back there. So there is a second cube. So this atom here is being shared by this cube here, the one in white, and then the one in blue that we've just drawn. But then there's also going to be another cube out here. Right, so we could draw that cube there. So now you could see this atom here is being shared by 1, 2, 3, 4. Well, if you think of 4 cubes here and then another 4 cubes on top, think of a set of cubes that I would draw on top of these. This fellow is actually being shared by 8 atoms, or excuse me, by 8 different unit cells. So if this here is our unit cell, how many atoms are in this cell? So how many atoms in, well, we wrote up here the unit cell. How many atoms do we have? Well, if every one of these fellows on the corner only counts as 1/8 of an atom because it's being shared by 8 unit cells. So just imagine a set of cubes, and that would be true for all of these atoms. So this guy only counts for 1/8. This only counts for 1/8 of an atom. This only counts for 1/8. So we started out, let's redraw it again. We started out with a unit cell that had 8 atoms. So we'll just kind of get rid of all the messiness we had further for that illustration. But this is being shared by 7 other cells. And this fellow is being shared by 7 other cells in addition to this one. So this counts as just 1/8 of an atom. So that's 1/8 of an atom. And now you can see that if we have 8 atoms all together here, right, 4 on top, 4 on the bottom, then the total number of atoms is equal to 8 times 1/8 equals 1. So this entire unit cell just counts as 1 atom. So if we have polonium in a simple cubic structure, which would look like this, these seemingly 8 atoms really only count as 1 total atom, and that's the value that we got for calculating Z in that prior equation. So it's kind of a weird situation, but it's really just because these guys are being shared by other unit cells, and so they don't count as a full atom. Now, if we had something on the edge maybe pause the video for a moment and think about how many unit cells that would be shared by. Now, we don't have anything on the edge. There's nothing there for the case of polonium. But if we had a series of boxes surrounding this fellow, then this would be shared by 4 different unit cells, and it would count as 1/4 of an atom. If we had something sitting in the middle of this fellow, then it would be completely contained within that unit cell, and that would count as a full atom. But we don't have that. For the case of polonium, we just have our simple cube where the atoms are directly on top of one another, nothing filling any of the interstices. All these count as 1/8 of an atom. We've got 8 of them, so we just have one atom in this thing here, which is the unit cell. And that unit cell is the smallest building block we need to build a model for the polonium crystalline material.